Hi everyone. So in this video I want to take you through some more technical aspects of limits. In particular, this is the more formal and precise definition of what a limit is. And while this is more advanced material, which generally goes towards courses like real analysis or advanced calculus, we're not going to get too deep into the forest here. So we are just skimming the surface. This is just a brief introduction to the more formal notion of limits. So yeah, so just as a warning, this is not going to be easy. And so don't worry if you don't quite get it all, or some of it seems unclear, fuzzy the first time you see it. Right, this is not something I'm going to emphasize all that much. Right, this is just to give you a little taste of what goes beyond calculus in more advanced courses. So the first thing I want to do before we actually get into anything about limits, I want to review absolute value. So this is something you've certainly seen before, right? The absolute value of x is just x if x is greater than or equal to 0, and negative x if x is less than 0. So nothing new there. But I want to make sure you understand statements like the absolute value of x minus 5 is less than 2, right? So what this is saying is that the distance away from 5 has to be less than 2, right? The way you can solve this is by essentially introducing negative 2 on the left, x minus 5 in the middle, and then 2 on the right. So when you add 5 to the middle and the left and the right, all this is saying is that x has to be between 3 and 7. Right? So if this is 5, right, x has to be no more than a distance of 2 away from 5. So going ahead, 5 plus 2 is 7, and going backwards, 5 minus 2 is 3. So as long as x is anywhere on this interval here, then this inequality is satisfied. Okay, so that's just for starters. Right. So the next thing, before we get to the formal definition of a limit, let's just review the definition we've been using so far. So if you remember, this is the limit as x approaches a of the function f of x is equal to L, if L is some number, right? And remember what this means, right? This means as x gets closer to a, right, gets closer to the number a, then f of x gets closer to the number L. Right? So we can just as well say as x approaches a, then f of x approaches L, right? And by approaching, we just mean we're getting closer and closer, right? So one thing that might have bothered you about this definition is, well, right, what do we really mean by getting closer, right? The question that that should be on your mind is how close? Right? So what does it mean to be close enough? Right? What counts as being close enough? Okay, so for example, if let's say x is approaching 17. Okay, so what's close to 17, right? And I mean, numbers like 16 is pretty close to 17, but we know we can get closer. We can do 16.5 or 16.8 or 16.9. And all these numbers are indeed getting closer to 17, right? 16.99, 16.9999. And these are getting very, very much closer to the number 17. And notice these are all less than 17. You can go from the other direction, right? From the positive side of 17. You can say 17.1, 17.01, 17.00001, and so on, right? So, intuitively, we know what it means to get close to 17, right? But, the question is this number close enough? We might want to get closer, right? Right? Is 16.9999 close enough, right? So this is what we're going to do. We're going to make this idea of being close to or approaching another number a bit more precise, right? And to do that, we're going to use these numbers that tell us the distance away from A, right? So in this case, our A is 17, right? So we're going to use these small Greek letters, delta, which is going to be some positive number, and epsilon, which is going to be some positive number. So this is the Greek letter delta, and this is epsilon. Okay, and they're going to represent small numbers. I mean, they don't have to be small, but if we want to get close to something, then right, these numbers are going to want to get smaller and smaller in general. Okay, so let's get to the formal definition of the limit. Okay, so the limit as x approaches a of f of x is equal to L, right? We're going to take this to mean the following. Okay, so if for any positive real number, let's say epsilon, right, so greater than 0, it's going to be positive, there is also a corresponding number delta, also positive, which could depend on epsilon, right? It might depend on what epsilon is. So in general, delta can be thought of as a function of epsilon. It doesn't have to be. It could be just a constant, but it might depend on epsilon, right? In such a way, right, so that in absolute value, right, f of x minus L, right, and we can think of that as the distance that f of x is away from L. We want this to be pretty small, right? So for a given epsilon, we want f of x to be no further away from L than epsilon. Okay, so this has to be true whenever x minus a in absolute value, again, that's the distance that x is away from a, we want that to be less than delta. Okay. Right, and we also don't want x to equal a. Remember, when we're talking about the limit here, right, x is approaching a, but we don't care what happens when x equals a, right? That's the whole idea of a limit is the limit does not care when x equals a. It's only what happens when x is near a or close to a. So for that reason, we want this absolute value of x minus a to be positive, to be greater than 0. Okay, so as I said, right, this is pretty confusing, right? So let's try to sort of go through this carefully and see what this means. So I'm going to draw the graph of just some function. This is my x-axis, my y-axis. And so we have some function, I'll just call it f of x, right? And I want to pick a specific value of a that x is approaching. So let's say a is right about here. So that's my a, right? And even though f of a is defined here, it doesn't have to be. So I'm going to make a little hole at x equals a, right? Just to emphasize that, right, we don't care what happens when x equals a. We only want to know what happens when we're close to a. So the limit, of course, would be this y value here. It's a coincidence, right? So I'll call this L, right? And as I've illustrated before, right, these values of x are getting close to a, then these values of y are all getting close to L. And that's from the left side. From the right side, if x is approaching a, then the y coordinates, right, the f of x, these values are approaching L, right? They may never get there, but you can get as close as you want, right? So that's the informal, right, idea of a limit. It's what we've been talking about earlier. But now we want to make this a little more precise. And here's the idea, right? So we're going to be given some number epsilon, right? It could be a big number, it could be a small number, right? But we're given that number. And the idea is we want our f of x's to be no further away from L than epsilon. So epsilon is sort of the distance away from L, right? So we can go as high as this number up here, right? So this will be L plus epsilon. And we can go as far down here. This will be L minus epsilon. Okay, so we want our f of x to be somewhere in this band, right? So f of x can be over here, right? It could be down here, right? It can even be very close to L, but it can't be down here, right? This is too far away. It's further than epsilon, right? So that's the idea. That's where we want f of x to be. Okay, so now the question is, well, what do our x's have to be? How far from a can x be? Right? So where can x be? Can x be over here? Well, if x is over here, then my f of x is way up here, right? And as you can see, that's too far away, right? My f of x is past L plus epsilon. It's further away from L than epsilon. It's a bigger distance, an epsilon distance away from L. So yeah, my x can't be way over there, right? And that's because it's not close enough, right? So let's make x closer to a, say right about here. And if we go up, and now this is my f of x right here. Let's go straight across. Yep, f of x is within this band here, right? You can think of this as this little band as just an interval, right? It's from L minus epsilon to L plus epsilon. So I've been calling this the epsilon band, right? But it's just an interval of y's, right? We want f of x to be inside that interval. We want this to be inside this interval. Okay, so in order to make that happen, right, we know that x can't be too far away from a, right? If x is too far away, then that means f of x will be too far away from L. Okay. So what we need to find is a delta. The delta tells us how far away we can go from a. So if this is my delta, so this would be, say, a plus delta, or I can go backwards, say a minus delta. I think I went a little too far. A minus delta. If I am within this band, let's see what happens, right? I go straight up, and I go straight across, and I'm still within L plus epsilon. And if I go straight up here and go straight across, I am still within L minus epsilon. So whatever delta this is, if my x is in this band here, right? If my x is inside the interval from a minus delta to a plus delta, you can see that's good enough because f of x will be within this epsilon band here. Okay, so that's the idea. Okay, now let's see if we can actually do an example of this. Okay, so using epsilon delta, we want to show that the limit as x approaches 2 of the function 4x minus 3 is equal to 5. Okay, so again, it's pretty clear that this limit is 5. I hope you realize that you can calculate this limit just by plugging in x equals 2 for x. But realize why we can do that, right? It's because 4x minus 3 is a continuous function, right? It's a linear function. All linear functions are naturally continuous, right? Okay, so, computing the limit is, by now, the easy part, right? Proving that this is the limit is going to be the hard part, right? This is where we're going to have to use these epsilons and deltas. Okay, so here's our goal. For any given epsilon, we need to find a delta, possibly that depends on epsilon, so that, right, if x minus a in absolute value is less than delta, then that's going to guarantee that f of x minus L in absolute value is less than epsilon. Okay, so that's the precise definition of a limit. And let's apply to our particular example here. In our example, a is 2, right? L is 5, and my f of x is this 4x minus 3. Okay. So let's write this statement down again, right? So for any epsilon, right, we need to find the delta, possibly as a function of epsilon. And what we want to guarantee is, as long as, right, 0 is less than the absolute value of x minus a, remember a here is 2, if that's less than delta, then that guarantees that in absolute value f of x, remember f of x in this case is 4x minus 3, minus L, in this case L is 5, that this in absolute value has to be less than epsilon. Okay, so how are we going to do this? Well, the first thing I would do is just look at this, what's in absolute value here, right? 4x minus 3 minus 5. Well, minus 3 minus 5 is minus 8. So this is just the absolute value of 4x minus 8. And we want that to be less than epsilon. Okay, so far? And notice that I can factor out the 4 here. This is 4 times x minus 2. In absolute value less than epsilon. And because 4 is a positive number, right, I can take it outside the absolute value. You should convince yourself of that I'm not doing anything wrong here. So we have 4 times the absolute value of x minus 2 is less than epsilon. So now this is looking a little more familiar, because if you remember, we want the absolute value of x minus 2 to be less than delta. And over here we have this absolute value of x minus 2, except there's one difference here. It's multiplied by 4. Okay, so not a big deal. Just divide both sides by 4. Right? As long as it's a positive number, the inequality stays the same. 4 divided by 4 is 1. And now we have the absolute value of x minus 2 is less than epsilon divided by 4. But remember, we want x minus 2 in absolute value to be less than delta. So it should be pretty clear that our delta should equal epsilon over 4. So let's let delta equal epsilon over 4. Okay. Now, remember, our goal is to get delta small enough so that this f of x is close enough to L, is within epsilon of L. right? So as long as delta is no bigger than epsilon over 4, certainly we can make it smaller, right? We can make it, I don't know, epsilon over 5 or epsilon over 6. But we don't want to make it any bigger because then, right, essentially we want to make sure that this is true, and this might not be true if we make delta too big. Okay, so this is sort of the cusp, right? We don't want delta to be any bigger. It could be smaller, but this is the biggest that delta can be that would ensure that f of x, the 4x minus 3, is within epsilon distance of the limit, which is 5. Okay? All right, so we made our choice, right? This is our choice. We're going to choose delta to be epsilon over 4. Right? So now I just want to check and make sure that, right, our goal is to ensure that this f of x is within epsilon of L. Right? So let's write this down. This is what we need to guarantee, right? That f of x minus L in absolute value is less than epsilon. Well, our f of x in this case was 4x minus 3, right? And we know that L is 4, right? Okay, I'm just saying the same thing again, right? So this is the 4x minus 8 is less than epsilon. Okay. Okay, so what we really want to do is work backwards, right? So we're going to suppose that x minus 2 is less than delta, right? This is the assumption. And what we want to conclude is this over here. We want to make sure that this is true. Okay, so remember our choice for delta was epsilon divided by 4. Right? So in absolute value, x minus 2 is less than epsilon over 4. And of course, x minus 2 should be positive, right? We want to make sure that x does not equal 2. Okay, so just multiply both sides by 4. No problem there. And I can bring the 4 inside the absolute value as well. And I can multiply through by 4. So I get 4x minus 8. In absolute value, that has to be less than delta. And I can split this apart. I can make it 4x minus 3 minus 5. Right? So what I have here now is in absolute value, I have f of x, right, minus L is less than epsilon. And this is what we wanted to show. So as long as this is true, we picked the right delta, right? The delta equals epsilon over 4 is just good enough. Okay. So there we go, right? We now showed that this limit up here is correct. Right? As obvious as that might seem to us, right? I mean, 4 times 2 minus 3 is equal to 5, sure. But remember, the limit is not saying that what happens when x equals 2. It's saying that if x is close to 2, then 4x minus 3 is close to 5. Right? And now we're making this more precise by saying, well, how close, right? How close does x have to be to 2 in order for f of x, the 4x minus 3, to be close enough to 5? Right? So that statement, close enough to 5, right? That's the L. We want it to be within epsilon. And epsilon, we can make epsilon to be whatever we want, right? So suppose epsilon is, again, usually we want it to be a small number, right? Because we want f of x to be close to L, so we want epsilon to be small, right? So what can we pick to be epsilon? Some small number. How about 0.04? That's pretty small, right? It's 1 over 25. Okay. So what that means is I want my function f of x minus L to be less than 1 over 25. I'll keep it as a decimal, 0.04. Right, now my f of x, of course, was 4x minus 3. My L was 5. Oops, 0.04. And so this is, right, 4x minus 8 is less than 0.04. Again, I can factor out the 4. And now divide both sides by 4. And I have x minus 2 in absolute value is less than 0.01, right? 1/100th. Okay, so in order for my f of x to be within 1/25th, right, 0.04 of L, this is the condition I need. This is my delta, right? I need to pick delta to be no bigger than 1/100, right, or 0.01. Right. So let's check that, right? What does this mean? X minus 2 is less, in absolute value, is less than 0.01. Well, it means that negative 0.01 has to be less than x minus 2, which has to be less than positive 0.01. Right? And if you add 2 to everything, you get that x has to be between 1.99 and 2.01. Okay, so if x is within this band, within this interval, right, here it is in interval notation. If x is inside this interval, does that guarantee that my f of x, right, will be within epsilon of L? Right? So that's what we need to show now, right? So if x is this close, if x is this close to the number 2, right, then we want to show that f of x, here we go, f of x, which is the function 4x minus 3, is within 0.04 of L. Remember, the limit here was 5. Okay, so let's see if we can do that. Right, so one way we can do that is just think of our goal, right? We want this absolute value of 4x minus 8, right, or 4x minus 3 minus 5 to be an absolute value less than or equal to, or sorry, not less than or equal to, strictly less than 0.04. Right. So if I just take this and subtract 2 from both sides, I get that in absolute value, x minus 2 is going to be between negative 0.01 and positive 0.01. Right? And now I can multiply everything by 4. Well, yes, 4 times 0.01. Right, so this is just negative 0.04 is less than 4x minus 8, which is less than 0.04, positive 0.04. Right? And now I just split this up into the f of x. Remember, f of x is 4x minus 3. And to get negative 8, I need to subtract another 5. Right? So this is my f of x minus L. Right? And it's between negative 0.04 and positive 0.04. And all that means is that in absolute value, my f of x minus L is less than 0.04, right? And that was my original choice, right? My epsilon had to be, or I chose my epsilon to be 0.04. So as long as x is between 1.99 and 2.01, that will guarantee that my f of x, right, will be, well, essentially between we'll be within epsilon. We'll be within 0.04. Right, because another way we could say this, right, the 4x minus 3 is the f of x, right? That's going to be between 5.04 and 4.96. Right. So as long as f of x is between 5.04 and 4.96. And that's essentially saying the same thing as this. Okay. As far as the picture goes, we can try to draw the graph here. And again, it could be very sloppy. So 4x minus 3, the graph will look something like this. All right. So it's just a straight line, right? Y equals 4x minus 3. And 2 is going to be somewhere over here, so that's my A. Right? And even though this is continuous, right? So if you plug in 2, you do get exactly 5. Right? The whole idea of a limit is what happens when x is close to 2. Right? So if I chose my epsilon to be, remember, 0.04, that means I want my f of x to be no bigger than 5.04 and no smaller than 4.96. That's the epsilon band around the limit, around 5. Okay, so we had to search for the delta, the corresponding delta, that will ensure that the f of x will be within this band. Right? And what we found is that if my delta is only 0.01, 1/100th, so if I'm 1/100th of a way from 2, either positive or negative, right? So between 1.99 and 2.01, if my x falls anywhere within that range, right? If this is my x in that range, then the f of x is guaranteed to be somewhere between 4.96 and 5.04. Okay? So that's the idea, right? This is what we wanted to show. Right, and as I said, this I admit this is going to be kind of confusing at first, so don't worry if you still don't have all the details down or couldn't quite figure out all of the calculations here. So I'm going to let you try one more example. Right, so using the epsilon delta definition, right, you want to show that the limit as x approaches 6 of the function 1/3 x plus 5 equals 7. Okay, so try that. Okay, so let's see, right? What we want to show is if x is within a distance of delta from 6, right? That's our A here, right? But not equal to 6. Then we want to guarantee that our f of x minus L is within epsilon. In this case, our f of x is 1/3 x plus 5. Our L is 7. And again, epsilon is just some given number, right? If you want to make up a number like, 0.08 or something like that, then that's fine. But for now, I'm going to leave epsilon as it is, and we can always plug in numbers later. Okay, so within absolute value, I have 1/3 x plus 5 minus 7 is just minus 2. And I can do the same trick I did with the 4 in the previous example with the 1/3. I can essentially factor out the 1/3 here. Right. And of course, 1/3 can come outside the absolute value. Right. And now just multiply both sides by 3. Right. So that cancels on the left. And what we end up with is the absolute value of x minus 6 is less than 3 times epsilon. And sure enough, if we want x minus 6 to be less than delta, then we should choose our delta to be no bigger than 3 times epsilon. Okay, so yeah, don't make it 4 epsilon or 5 epsilon. You can make it 2 epsilon or even just 1 times epsilon. Right, anything smaller should work. Anything bigger probably won't work. right? So this is going to be our choice. This is what we're going to choose our delta to be. Right? And now we just want to make sure that this is correct, right? We want to make sure that as long as an absolute value, right, the absolute value of x minus 6, again, assumed to be positive, is less than delta, then that's going to guarantee that f of x minus L with an absolute value will be less than epsilon. Okay, so yeah, our choice was, again, but by this calculation, right? I mean, it wasn't so much a choice. It was dictated by doing this calculation here that we got delta to be 3 times epsilon. Right. But we could choose it to be something less than that as well. Right. Okay. So this is going to be less, x minus 6 in absolute value will be less than 3 times epsilon. Right. So if I divide both sides by 3, and I put the 1/3 inside the absolute value, I get this. In absolute value, 1/3 times x minus 6 is less than epsilon. And if I distribute the 1/3, I get 1/3 x minus 2 is less than epsilon. Right? And remember, our original function was 1/3 x plus 5. So let me break off a 1/3 x plus 5. But now to get to -2, I need a -7, right? 5 minus 7 is -2, and that's less than epsilon. And what that gives me is, if this is my f of x, and the 7 is my L, I have an absolute value f of x minus L to be less than epsilon, which is what we wanted to prove in the first place. So it turns out this choice of delta, 3 times epsilon, right, was certainly good enough. Okay, so that's it. That's all we had to show here, right? It's basically 2 steps. First, figuring out what delta has to be, right? And that's starting with what we want to happen. This is what we want to happen, right? And then by making this choice, right, for this delta, this is what we need to happen, right, in order for what we want to happen to actually occur. Okay? All right. So that's it for this. And what made this reasonable, I'm not saying it's easy, but it's a reasonable problem, is the fact that the 2 functions we dealt with so far were just linear functions. Right? So if f of x is just mx plus b, you can kind of see what happens, right? It has to do with the steepness of the line. Right? This line was not all that steep, right? It had a slope of 1/3. So for a given value of epsilon, you can see that we can be considerably further away than we were in the previous problem, right? If the slope is very steep, then delta has to be much smaller for the same interval, if that makes sense, right? Yeah. So I'm going to do an even harder one now. This is going to be not a linear function, but a quadratic one. Okay, so this will be our last example. And this is definitely going to be a more difficult one. The argument we're going to have to use here is a bit more subtle, right? So using the epsilon delta definition, we want to show that the limit as x approaches 1 of the function x squared plus 3x is equal to 4. Okay, so again, let's write down what we know. We know our function f of x is x squared plus 3x. We know our a here is 1, and our limit is 4, as you can easily verify. Right? And so what we need to show, right? So for a given epsilon, I'll call it given, some given number epsilon, right? We need to find a delta. We need to find a delta, again, possibly depending on epsilon, so that as long as the absolute value of x minus a, so x minus 1, an absolute value is less than delta, then that's going to guarantee that my f of x, x squared plus 3x, minus L is 4, will be less than epsilon, again, an absolute value. Okay, so remember how this works, right? We're going to have to pick some delta, depending on epsilon, that will guarantee this statement here, that our f of x is within epsilon of L. Okay, so by working with this, playing around with this, we should be able to somehow figure out what delta needs to be in order for that to happen. Okay, so notice that there's no factors here. There's no common factor to take out. However, x squared plus 3x minus 4, right, can be factored as x minus 1 times x plus 4. Right? And right, the absolute value of the product is the product of the absolute value. So I could write this as the absolute value of x minus 1 times the absolute value of x plus 4 is less than epsilon. Again, you should convince yourself of that if that's not clear. Okay, so now comes the tricky part, because it might be tempting to say, well, you know, I'm looking for the delta here, right? The absolute value of x minus 1. So you might just say, well, let's just divide by the absolute value of x plus 4. Right? And so my delta should be epsilon over the absolute value of x minus 4. Unfortunately, that doesn't work, because remember, delta can certainly depend on epsilon, right? But it cannot depend on x. Cannot be a function of x, right? So yeah, so we can't just divide by the absolute value of x plus 4. Okay, so this is where the argument gets a little bit subtle. So I'll try to go through this carefully, and let's see what we can do here, right? So sure, remember, we need to pick a delta, right? And I could make delta essentially to be anything I want. And, you know, it may or may not work. Remember, if delta is too big, if I pick delta to be, you know, 300, depending on what epsilon is, that, right, this might not be enough. This condition might not work. It might be false, right? So I'm going to start with a reasonably small delta, right? A small number, but a simple one, right? Just the number 1. Right, so I'm gonna choose, at least for now, for delta to be just equal to 1. And let's see what that means, right? It means that 0 is less than the absolute value of x minus 1, which is less than 1. Sorry, it's absolute value. And that means that x minus 1 has to be sandwiched between -1 and 1. Oops. Again, we're assuming that x does not equal 1 here. That's why this is greater than 0. So x does not equal 1. Right. And now just add 1 to everything. And what that tells me is that x has to be between 0 and 2, right? Except equal to 1. At some point, I'm not going to say that anymore. We're just assuming that, right, x is not equal to 1. Remember, in the limit, as x approaches 1, we don't care if x equals 1 or not. Right? All right, so now, if x is between 0 and 2, what does that mean for x plus 4? Right? If I add 4 to the middle, I have to add 4 to the right and add 4 to the left. And I get that x plus 4 is between 4 and 6. So, right? So in order for this to happen, the absolute value of x plus 4 certainly can't be bigger than 6. Right? So it has to be less than 6. And yes, what I've also done is expanded what x could be lower than that, right? In other words, right, x could be, I'm sorry, x plus 4 could be less than 4 in this case, right? But remember, we want to be fairly liberal here, so we can ensure that this statement is true as long as x plus 4 in absolute value is less than 6. Okay, so now, right, let me go back to this, right? The absolute value of x minus 1 times the absolute value of x plus 4, right? That's going to be, oops, sorry, it's not going to be equal to, it's going to be less than the absolute value of x minus 1 times the number 6, right? And remember, we want this to be less than epsilon. So if I divide by 6, I get that the absolute value of x minus 1 is less than epsilon over 6. So there you go, right? Now we have our delta. Our delta should be, right, epsilon over 6. Let's just stipulate that delta equals epsilon over 6, or something smaller than that, right? Right. Remember, when you do this, this is always sort of the cusp. This is the biggest that delta can be, right? It can certainly be smaller, but we don't want it to be any bigger, because if it is bigger than that, then again, this statement here might not be true. Okay. Now wait a minute, you might think. Didn't I earlier just choose delta to be equal to 1? So how am I getting delta to be this epsilon over 6, right? Which is it? So remember, we want delta to be small enough so that this statement has to be true, right? Again, this statement is my original f of x minus L in absolute value less than epsilon, right? We want to guarantee that that's the case. So, right, so which delta we pick, we want it to be as small as possible, right? So we're going to choose our delta then to be the smaller of these two numbers. The smaller of either 1 or epsilon over 6. Whichever one is smaller, that's the one we're going to pick, right? So another way to write this is we're going to choose delta to be the minimum, right, of the set of either 1 or epsilon over 6. Okay, so that's our choice, right? Right. So let's see what happens, right? So if this is our choice, again, what we want to guarantee, what we want to prove at this point is this statement here, right? That f of x minus L, right, is within epsilon, right? Or f of x is within epsilon of L. Okay, so that's what we want to show. So let's start with, let's suppose epsilon is pretty big, and let's suppose that the minimum of the two is 1. So like if epsilon is equal to, let's say 12, then we're picking the minimum of 1 and 2, right? The smaller number is 1. So let's for now, again, let's just suppose that epsilon is equal to 1, right? So remember what that means? It means that x is between 0 and 2. Okay, right? And so what is f of x going to be here, right? What will my f of x band be? How far from L will it be? In this case, L, of course, is 4. So how far from 4 can we get? Right. Right. So remember, the equivalent here, right? If epsilon happens to equal 6, then that's the same as delta equals 1 as well, right? So just keep that in mind. Okay, so yeah. So x is between 0 and 2 with this choice of delta, right? Either epsilon equals 6 or delta equals 1, right? And remember, that means that x minus 1 in absolute value is going to be less than 1. Okay. But remember, it also means that in absolute value, x plus 4, right, is going to be less than 6. So if I multiply those, right? X minus 1 times x plus 4, again an absolute value. That's going to be less than 1 times x, right? And remember, I can combine them. I can multiply the x minus 1 times the x plus 4. And if I expand that out, I get an absolute value, x squared plus 3x minus 4 is less than 6. Right? And that should do it, right? Because the x squared plus 3x, that's my f of x, and the number 4 is the L. So this has to be less than 6, which is epsilon, right? Remember, epsilon equals 6 was our choice here, right? Equivalently, delta equals 1, right? So this works, right? This guarantees this condition. Okay, right. So now let's suppose, right, this was under the assumption that delta is equal to 1. But what if the smaller number is this epsilon over 6 here? What if that's smaller? Okay, so now let's choose delta to be epsilon over 6. Right? Which, remember, epsilon then has to be less than 6 for this to work. Okay, so right, we're going to essentially go through the same argument here. Sorry. So, yeah, so the absolute value of x minus 1 times the absolute value of x plus 4, right? So the absolute value of x minus 1 is less than delta. Maybe I'll put that on the left here. Right, so this is less than delta, which is epsilon over 6. But remember, the absolute value of x plus 4, right, has to be less than epsilon. I'm sorry, I didn't mean epsilon. I meant 6, right? Remember, absolute value of x plus 4, way up here on the upper left, right? That has to be less than 6. Right. So we get 6 epsilon over 6. The 6's cancel, and this is still equal to epsilon. Right? And then by expanding all this out, we again get the absolute value of x squared plus 3x minus 4 is less than epsilon. Right. So we just showed the same thing. Right. So what we showed is that it doesn't matter. As long as you pick your delta to be the minimum of these two numbers, either 1 or epsilon over 6, right, then that's going to guarantee that our f of x, the x squared plus 3x, will not be further away from 4 than a distance of epsilon. Okay? Right. Again, at this stage, if you're still not convinced, play around with it, right? And start making up a number, right, for epsilon. Right, so suppose epsilon, again, I kind of want to make it a nice number here, right? How about 0.6? Right, if that's my epsilon, then you have to pick the corresponding delta. What should delta be? And then just make sure with that choice of delta, right, that, right, your conclusion then, with this choice of a positive delta, the conclusion has to be that f of x minus L with an absolute value would have to be less than epsilon. Right, in this case, 0.6. Right. So, yeah, remember, so epsilon over 6 then would be a nice number. That's why I picked 0.6. So epsilon over 6 would just be, 0.1 or 1/10. Right? And remember, we want the minimum of 1 and 1/10. 1/10 is certainly less than 1, so that right. So we're going to have to use 1/10 for this, for our delta. That, again, 0.1 works. So, right, our delta is going to be 0.1. So, in absolute value, x minus 1 should be less than 0.1. Right? And as a practical matter, that means that x is between 0.9 and 1.1. So if x is within this band, that should guarantee that our f of x is not that far away from L. It's within epsilon of L. Okay. And we could go through the same argument again, or we can think of it this way, right? If we look at the graph, and it is helpful to draw the graph here. So this is 1, 2, 3, -1, and so on. And I'm going to squash the y scale, so this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. Well, okay, all right. This might be a little too squashed, but let's see what happens, right? So the graph is going to look something like this. We know it goes through the origin. When x is 1, y is 4. When x is 2, y is 10. And so I think when x is -1, it's -2. So it's going to be a parabola, something like this. Right? And the important thing, right, the limit we know is 4 as x approaches 1. Okay. So we've chosen epsilon to be 0.6. So what that means is, right, my f of x can't be bigger than 4.6, and it can't be less than 3.4. Right, does that make sense? I mean, let's check. Right, so f of x minus L is 4, is less than 0.6. So just do the usual thing here. And when you add 4 to everything, 4 minus 0.6 is 3.4. Right, and 4 plus 0.6 is 4.6. So that's where I got these numbers from. Right. So that's the interval, right? F of x should be between these two numbers, 3.4 and 4.6. Right. So we go across and we go down, and you can see this is going to be a very narrow band here. I'm exaggerating considerably, right? So if I did pick my x to be, what's the lowest value of x I can pick is 0.9. In fact, it has to be bigger than that, but let's say we're on the cusp and we pick 0.9, right? So if I plug in 0.9, my f of x should be, well, it should be bigger than 3.4. Let's check that, right? If I plug in 0.9 into the function, remember the function was x squared plus 3x. So 0.9 squared plus 3 times 0.9. And I get 3.51, right, which is bigger than 3.4. So we are within that band, right? So that makes sense, right? And my biggest value of x that I could pick is 1.1. In fact, it can't be even 1.1. It has to be less than that. But let's say we're right on the cusp here, and I plug in 1.1. What I'm hoping to happen is that I get a value of f of x here, the y value, will be somewhere between 3.4 and 4.6. So it has to be less than 4.6. So let's just calculate this. My calculator says 4.51. That's nice. Yeah, 4.51 is less than 4.6. Right, so it is within that band as well. So, yep, so this interval here, this condition here, that my x is between 0.9 and 1.1, that is with a delta value of 0.1, right? So I'm 0.1 away from 1. Then that's going to guarantee that my f of x, right, will be no further away from 4 than 0.6, right? So it can be as big as 4.6 or as little as 3.4. And in fact, we know it's actually going to be even more constrained. It's going to be even further inside that interval. Okay, right. In fact, yeah, with this interval, we know our f of x will actually be between 3.51 and 4.51. But that's certainly going to be contained in the interval from 3.4 to 4.6. Here, let me rewrite that because that's a little sloppy. Right. So if x is between 0.9 and 1.1, then by the calculation we just showed, x is going to be between 3.51, sorry, f of x will be between 3.51 and 4.51. Right. But all we needed it to be, right, our given condition here was we needed this to be between 4.6 and 3.4. And so it is. Right. So that's it. Again, I know this is tricky, especially with this, first picking delta to be 1 and then later finding it to be epsilon over 6 and then just taking the minimum of the two. It's a little bit subtle. So I really wouldn't worry about that. Especially if you can do examples like 1 and 2 with the linear functions. Those are more routine because the math works out a lot better than this, right? It's because this was a quadratic function, the x squared, that ruined it, right? That made this a bit more difficult. So as I said, I'm not going to emphasize this, but it does answer sort of the lingering question. When we originally defined the limit, we used words like approaching and getting closer. And right now we answered the question, how close do we need to be, right? So how close does x need to be to a, right? Ensuring that f of x is close enough to L. Okay, so the answer is within epsilon, right? And x has to be within delta away from a. Okay, so that's where we need this epsilon and delta argument. And again, it's essentially going to be used to prove limits like this. But proving things like that is usually more for an advanced course. So as I said, if you didn't follow this, I wouldn't worry about it too much, right? I'm much more concerned with can you calculate the limit in the first place, right? Right. Can you calculate the limit as x approaches 1 of x squared plus 3x? Because that's one of the easier ones you're ever going to see, especially because it's a continuous function and you can plug in the number to evaluate a limit of a continuous function. Right. So I hope this helps, or at least I hope this is reasonable. For those of you who really are interested in sort of more the abstract version of calculus, which is called analysis, this is something you're going to use over and over again in your more advanced courses. So I hope that will help at least give you this sort of idea for that.